So, in the last lecture, we have discussed the magnetic dipole moment. So, simply we have seen that what we have seen in our previous lecture that the electron, because every material has a certain magnetic properties, and you know that when the charge is in motion, it produces a magnetic field around it. Now the question is that how the magnetic field is produced by the moving charge, one thing. The second thing is that the motion of the electron within the atom possesses two types of motion. One is the motion around the nucleus, which we call it as the orbital motion, and the second motion is the electron spinning in its own axis, which we call it as a spin motion. So these both motion gives rise a magnetic field. So now we have to look at what is the magnetic dipole moment due to the motion. First, we say that this is the nucleus and electrons are is orbiting around the nucleus. This is the electron which is orbiting around the nucleus. So as a resultant, the electron is orbiting in this direction counterclockwise. It generates a magnetic moment whose direction is upward. This magnetic moment is due to its orbital motion, so we call it as a mu L. And this mu L magnetic dipole moment is equal to current times the area of the loop. And we have seen that this current is equal to the flow of charges per unit time, and area of this loop is equal to pi r square. R is its radius. So here this t is the time period which is equal to, this is the electron, so therefore the negative sign indicates the motion of the electron. So E, this is the time period which is equal to the circumference 2 pi r upon the velocity into pi r square. So this can be rewrite as this v goes to up, so r 1 r cancel, pi cancel. This is equal to minus 1 upon 2 e r and v. So this is the mu L, magnetic moment of the moving electron. So here this mu L is equal to, mu L is equal to, this mu L is equal to this relation. So now multiplied and divide with m, this gives rise mu L is equal to minus 1 upon 2. If we divide with m, we have to multiply with m, and this is equal to mvr. This here, if we multiply it here, mvr. This mvr is the angular momentum, mvr is the angular momentum. So here, this m is the mass of electron, v is the velocity of the electron. This electron is rotating with the velocity v in this direction. V is the velocity of the electron, and r is the radius of the orbit. So here this is equal to L, L is equal to mvr. So therefore the mu L is equal to minus E over 2m into L. This is known as a magnetic dipole moment of a electron due to its orbital motion. So the total magnetic dipole moment is due to the orbital motion and due to the spin motion. So the magnetic moment due to the spin motion is known as intrinsic magnetic dipole moment. Here the total magnetic moment is equal to mu L plus mu S. So this mu S shows that it is the intrinsic magnetic dipole moment. So here this mu is equal to mu L, which is equal to minus E over 2m into L, plus mu S, which is equal to E over 2m into 2s, because spin has two options, two possibilities, either spin up or spin down. So therefore here 2 to cancel, so the mu total magnetic moment is equal to E over 2m into L plus E over m into S. So this is the total magnetic moment due to the orbital motion and due to the spin motion. This is what we have discussed in our previous lectures. So now we have to look at, okay, how the material behave as a magnet. What are the magnetic properties of the material? So now you know that every material has a certain magnetic properties, because this mu, which is the magnetic dipole moment, is associated with the magnetic property of a material. How we have to look at? So here we have to see that what is the magnetization. How to define a magnetization? You know that every material has a certain magnetic property. For example, let's say this is the material and it consists of the atoms. These are the atoms, let's say. So now each atom has a certain magnetic property. Let's say its dipole moment is in this direction. It means this is the small magnet which has this north pole and this south pole. Similarly, if we say that this is an atom, it has a dipole moment, we say that its dipole moment is in this direction. So this is the magnet which has two poles, north and south. Similarly, again this is the magnet whose dipole moment is in this direction. So therefore this is the north pole, south pole. This is the magnet. It means each atom acts as a tiny magnet. So now if these tiny magnets which are oriented, whose magnetic field is oriented in different direction, so as a resultant they will cancel out the effect of each other. So the resultant magnetic field is zero because they are randomly oriented. When they are randomly oriented, it means the net magnetic field is zero because one of the direction of the magnetic dipole moment will cancel with the other. If we say that this is the magnetic moment in this direction, if we say that there is a magnetic moment whose direction is this, so as a resultant they will cancel each other. Similarly, they will cancel each other. So in general, we say that this material is a non-magnet material. But every atom individually, microscopically, each atom act as a small magnet. As a whole, the magnetic property of one atom is cancelled out by the other atom. So as a resultant, as a whole, as a bulk material, the magnetic moment is zero. So this material is non-magnet material. So now question is that when this material is placed in the external magnetic field, we say that this is the B. This B is the external magnetic field. This B. B is the external magnetic field. When this material is placed in an external magnetic field, as a resultant, this external magnetic field will exert force on the magnetic moment. So, as a resultant, this will try to align the magnetic dipole moment in the direction of the magnetic field or opposite to the direction of the magnetic field. So, as a resultant, when the material is placed in the external magnetic field, when the material is placed in the external magnetic field, it exerts force, it produces torque to align the magnetic dipole moment in the direction of the external magnetic field. So as a resultant, torque tau is equal to mu cross B. So as a resultant, the magnetic field is produced. As a resultant, these will align in the direction or opposite to the direction of the magnetic field. So as a resultant, we say that the material is magnetized. It means now almost maximum or almost all of the magnetic dipole moments are rotated. Torque, due to this torque, due to this torque, which is called the turning effect of the force, as a resultant, these magnetic dipole moments will turn it along the direction of the magnetic field or opposite to the direction of the magnetic field. So as a resultant, now we say that this material is magnetized. Because of the external magnetic field, this material is now magnetized. Simple example I'm giving you: if you place a small piece of iron with a magnet for a moment, then if you replace the magnet, this small piece of metal or iron act as a magnet, because now the small piece of iron is magnetized till the thermal equilibrium is restored. So as a resultant, we say that this material is magnetized. So the magnetization is defined as the magnetic dipole moment per unit volume. So the magnetization is defined as the magnetization is defined as magnetic dipole moment per unit volume. In magnetization is the magnetic dipole moment per unit volume, which is equal to mu upon V. So this V is not a velocity, this V is the volume. Or magnetization M is the sum of all the magnetic dipole moment per unit volume. This summation over mu is the sum of all the magnetic dipole moments per unit volume. So now the total magnetic field here, this is the external magnetic field. We say that this is B naught. B naught, what we have seen is the external magnetic field. So now the material is get magnetized. When this material is now in the external magnetic field, the total magnetic field is equal to the external magnetic field and the magnetic field due to this magnetization process. It means now when the material is aligned, it will generate its own magnetic field. So within the material, now the total magnetic field is the magnetic field of the material plus the external magnetic field. So the total magnetic field is equal to the magnetic field of the material and and the external. So this B is equal to B naught plus this B naught is the external magnetic field and the magnetic field produced by the magnetization is equal to Bn. So here Bn, so here B is equal to B naught plus Bm, and this Bm is the magnetic field produced due to the magnetization process. So the total magnetic field is the original, external, and the magnetic field produced by the magnetization. And you know that this Bm is equal to where this magnetic field produced by the magnetization is directly proportional to the magnetization. Magnetic field is directly proportional to the magnetization. It means if we increase the magnetization, as a result, then the magnetic field will also increase. So this Bm is equal to proportionality is replaced by some constant and which is equal to mu naught, and mu naught is the permeability of the free space. So therefore this B is equal to B naught plus mu naught into A. So this is equal to B, and B is equal to this B, the total magnetic field can be rewrite as the total magnetic field can be rewrite as B is equal to K of M. K of M is a constant into B naught original. It means K of M, or we call it as a kappa M, is the permeability of the medium of the medium. Permeability of the medium. Km is the permeability of the medium. So here B is equal to Km into M naught. So here substitute this value in equation number 2. We get substitute this value in equation number 2. So therefore the equation number 2 becomes so B is equal, if we put it here, B is equal to Km B naught is equal to B naught plus mu naught M. So this can be go into this side and becomes minus. So as a resultant, this is the Km B naught minus B naught is equal to mu naught M. So B naught common, so this can be written as Km minus 1 B naught into mu naught into M. So here this Km minus 1 is typically of the order of typically of the order of 10 raised to power minus 3 to 10 raised to power minus 6 for most non-magnetic materials. So if we look here, what we have seen that, if we conclude it, we have seen that this is the material and these are the atoms of the material. Each atom has a certain dipole moment. As a whole, this material is a non-magnetic material because the dipole moment of one atom whose direction is in this direction can be cancelled out with the dipole moment of the other, because all the dipole moments are they randomly oriented. They are not oriented in the same direction. They are not aligned. So therefore, as a resultant, the magnetic moment is zero. Now, if this material is placed in a magnetic field, external magnetic field, as a resultant, most of the magnetic dipole moments aligned in the direction of the magnetic field. So when they are aligned in the direction or opposite to the direction, as a resultant, we say that the material is magnetized or magnetically polarized. We may call it as a magnetically polarized or magnetized. And the phenomena is known as a magnetization. It means the dipole moment per unit volume, they are now aligned in the external magnetic field. So now the total magnetic field is the external magnetic field plus the magnetic field of the material. So now when they are aligned, the magnetic field of material is non-zero because now they are not randomly oriented. They are oriented in the particular direction. So we have seen that the total magnetic field is the external magnetic field plus magnetic field due to the magnetization. Magnetic field due to the magnetization is directly proportional to the magnetic moment, magnetization, and mu naught is the constant. We have substituted the value of this over here. I have just substituted the value of this from here to here. But another relation, this total magnetic field of a material is equal to Km into V naught. It means the magnetic field is directly proportional to the external magnetic field. And Km is a constant which we call it as the permeability of the medium now. I just substitute this value over there, and simple mathematics tells us that K minus M B naught is equal to this. This is the phenomena of the magnetization, and K minus 1 for the non-magnetic material, its value is 10 raised to power minus 3 to 10 raised to power minus 6. So this is the end of this topic.